Well, good afternoon, everyone. Good afternoon. Welcome. It's absolutely fantastic to see a turnout. It's such a beautiful day. Thank you for coming inside, and we appreciate that. My name's Ross Virginia. I'm the director of the Institute of Arctic Studies here at Dartmouth. I'm also a member of the Environmental Studies program. And today's lecture is sponsored by the Institute of Arctic Studies and the IGERT seminar series on dialogues in polar science and society. It's a real pleasure to welcome back to Dartmouth Dr. John Hobbie. John is a distinguished senior scientist at the Marine Biological Laboratory Ecosystem Center located in Woods Hole, Massachusetts. He's internationally known for his research on the relationships between microbes, the little things that live in soils and lakes, and what they do in controlling nutrient cycling and productivity in ecosystems. He's done this in a number of ways. He's developed some of the foundation techniques that everyone in limnology today and microbiology know of and have used. But in pioneering these techniques, he developed a set of really fundamental and important questions, which really has positioned him as one of the leading microbial ecologists in the world. He received his undergraduate education right here at Dartmouth College. He's a member of the class of 1957. And 1957 was a very vibrant time. It was the third International Polar Year, all right? Villemir Stephenson was at Dartmouth College. The Northern Studies program was one of the most popular majors on the campus. We don't quite see it that way today, but that was a really great thing going on here at Dartmouth. And a lot of really prominent and important people that went to the North in different ways, scientists and politics and law, you name it, really came out of this period of Dartmouth's development. John sort of started this in 1957. He ended up in Greenland, right, with a group of Dartmouth students, measuring the thickness of ice on lakes in northern Greenland. And those of us who work in polar systems, at some point in our lives, we get what we call polar fever. And I don't know if that was it. Was that the start, or did it come later?
Just then, right?
Yeah. So John's had it for his entire career, obviously. He's gone on to spend most of his career trying to figure out how Arctic ecosystems work and how now they're responding to climate change. He started his work in Barrow, Alaska, but he quickly moved south a little bit to a place called Toolik Lake. And John really began to draw attention to this place scientifically from his research. And more people sort of came to Toolik Lake. And it's now really one of the best studied Arctic places in the world. And it's the site of the U.S. main Arctic research station. As part of that, John was a leader in pulling together something called the Toolik Lake, the Arctic Tundra Long-Term Ecological Research Program. There's like 20 plus sites that are there to establish long-term ecological baseline information. And there's one in the tundra, and it's at Toolik Lake, and John has been principal investigator on that project and really a driving force in all of the research that's come out of there. I think one of the special features of John's career is his impact on the development of ecosystem science as interdisciplinary science. In the early 1980s, a group of people came together to found the Ecosystem Center at Woods Hole. And I think it was if I interpret the history correctly, it was a group of scientists who were really committed to intensive teamwork, interdisciplinary approaches, but they also felt that the kind of university structure might hold them back a little bit. And the Ecosystem Center came to be one of these places where people came to focus on that in this very intensive collaborative research enterprise formed by scientists for scientists. And to this day, that model still exists at the Ecosystem Center and is highly productive. John's received many different honors from his peers in recognition of his research. He received a 2008 Redfield Award for Distinguished Lifetime Achievement by the American Society of Limnology and Oceanography. The Odom Lifetime Achievement Award. The word Odom, if you're in ecosystems, that's the gold standard. So any award with Odom on the front of it, I'm very excited about. And he's also a fellow in the American Academy of Arts and Sciences. John's worked throughout the world. It's not just the Arctic. He's worked in the Antarctic. He has a very strong research program in estuarine ecosystems. He's very interested in the coastal margin and microbial processes there and human impacts. But shortly after finishing up his graduate work, he went from Dartmouth, he went on to Berkeley and then Indiana University. John ended up far south in the dry valleys near McMurdo Station. It took me 27 years after John to get to that same place. I have polar fever and I still work in that area. John, I think, realized perhaps it wasn't quite green enough or biological enough or something or other, but he left the dry valleys and went north and has stayed up in the Arctic. But the U.S. Advisory Committee, and one of the things that can happen in Antarctica is if you work there and you're lucky, you might have a geographic feature named after you. All right, so I went online to make sure I knew there had to be something named Hobbie in Antarctica. So I went online and I found Hobbie Ridge. All right, Hobbie Ridge. And this is the official citation. It says a bold ridge. It's not any ridge, it's a bold ridge. And I thought that was prophetic because I think it really sums up John's approach to his science, to the way he works with students and his colleagues, and really the impact that he's made on his field. So it's a real pleasure to have John Hobbie back to Dartmouth to talk about the Arctic and what's happening to the Arctic. The title of his talk is Climate Change Threatening Alaska and Beyond? So please join me in a very warm welcome for John Hobbie.
Thank you, my boy. Thank you. All right, let's make sure the sound's on. Are we happy? Thank you very much, Ross, and the Dartmouth community here. The last time I got paid by Dartmouth to do anything, 1958, and I was a graduate student at Berkeley, and there was the Dartmouth expedition and USGS, and they're going to Alaska where I could do some thesis research. That was great, and they said, let me say again, I was a graduate student. I had no money whatsoever, and Dartmouth, in their kindness, said, yes, and we'll pay you when you get back. So I looked around for friends, and there was a very attractive blonde who was also at the practice studio. I was taking cello, and she was a pianist. And she was a school teacher, just gotten a job, $3,900 a year. Boy, that was money. And so I borrowed $250 from her, kept in touch, paid her back, and married her into the next year. So that was a good well, anyway, I hope Dartmouth has evolved from.
We'll see.
I'm going to tell you a little bit about the general, some changes that have been going on in Alaska just as a result of the temperature change. And certainly there has been temperature change. Here we see the annual temperature throughout the whole state, and has gone up. It's gone up to this point, it's gone up 2.5 degrees or so Fahrenheit. And because this is a general talk, I've tried to make it Fahrenheit. And the projection then, we see 5 to 13 Fahrenheit change increase by the end of the century. It's big. Now I point out Alaska here has areas of continuous permafrost up in the north, discontinuous and sporadic permafrost down here. And I'll tell you more than you want to hear about permafrost, because that's a really important part of the picture. And here are some of the places I'm talking about. Prudhoe Bay, where the oil company is here. Barrow at the tip. Fairbanks in the center of the state. Anchorage down here. And the Kenai Peninsula, this region here. So I'm going to mention some of these places. And on the North Slope, where I've done most of my work, the Barrow is up at the top, flat coastal plain, foothills, the Brooks Range, the mountains here, and we have a town of Dead Horse where the oil is at Prudhoe Bay, and the pipeline sort of follows this Sagamon-Irtok River here, all the way down to Fairbanks, and so we can drive there, which is the real important point, save lots of money. This part here is the Arctic National Wildlife Refuge, about this part here going on down south, and of course they just celebrated its 50th year. You should get up there if you ever can. Fairbanks, frost-free days, increased by 50% over 100 years. Nice long record in Fairbanks going back 1900. Certainly warming, but look at the variation from year to year. Number of frost-free days going up. Very difficult to take an average if you just have short term. Here you can see a change over 100 years. But snow cover at Barrow disappears 2 weeks earlier. When I was doing a lot of work up there, we thought it was around the 15th of June, the snow cover. Well, I was there in the 70s, and now snow cover disappears as early as 24th May. So there is certainly a change. Again, a lot of variability. The ice is changing in the Arctic Ocean, and one of the big problems that the walrus has, instead of the young with their mother going out on the ice floes, well, the ice floes are now tremendously far out, and the water is too deep out there for the walrus to eat on their bottom fauna. So they are hauled out on the shores of northern Alaska. So that's a new thing to happen. Don't know whether they're going to be able to survive like that, because it's a long way to the nearest flow, to the nearest food sometimes. There is a slight change in the commercial marine species in the Bering Sea, etc., that it's moving north, but they said it's between 1982 2006, it's moved 19 miles, the center of some of these populations. Caribou haven't really shown too much change yet. This is the porcupine caribou herd, and in the Arctic National Wildlife Refuge. So this is when they are on the coastal plain, and this is the foothills. Here's a picture I took in 1958. The herd was right there, and it circled this whole lake. And I always thought, before I went, well, it's easy to estimate how many caribou are in a herd. You just sort of take this many and then see how many this many there are. And so I don't know whether they're 10,000 or 30,000, but there are a lot of caribou there. And they would suddenly, a group of 1,000 or so would suddenly decide to swim across this lake for no good reason, and one or two might die. This particular group, you can see, I was just standing there. They were not afraid. A grizzly bear just walked through, had just gotten through walking through that. They sort of spread apart a little bit, and the grizzly bear just walked on through in this midnight picture. The ice is changing. So one commercial difference is going to be that ships are going to be able to reliably move across the northern sea route around Scandinavia, across northern Russia and Siberia. That they can do it now with little help from an icebreaker or two. And it's going to make a big difference if they can do it for a number of months. Well, on the North American side, there's a northwest passage that starts over here, going up past Greenland and Baffin Island, and then goes around a couple different routes around big Victoria Island here, and then around Alaska. A couple years ago, here in Tuktoyaktuk, there suddenly a Chinese ship showed up, and people got off and landed illegally, and then they got back on the ship and went off again. No one knows what they were doing there. But that's not, the Northwest Passage is not really open yet, or for a number of years. Here is the present. You can just go on the web. This is where the ice was in August, just a month ago, this is the time in August of the maximum drawback of the ice. It completely fills the Arctic Ocean rest of the year. In the summer, it draws back. Well, here is sort of the mean conditions from 1979 to 2000, and we see that there's been a lot of drawback already. And the commercial northern sea route, it was pretty well open all this time. However, the Northwest Passage here has still some blockage places. It's going to take a while more. This is just the extent showing a continual decrease in the extent. This is million square kilometers. And it's just going down, down, down. So it should be open within a few years. There was an interesting way of thinking about it. So this is more geography, sociology, asking the question, if you are in a settlement in the Arctic in November, how long does it take you to get to the nearest settlement, the closest settlement to you? And this could be walking across a river, a snowmobile ride on a frozen river, or rail, permanent road, shipping. So here is compared November in 2 years, November now versus November in 2045. The black areas is where you can't get there. You can't get to the nearest settlement at that time of year. The ice hasn't frozen enough to walk, and here there's no movement out in the Arctic Ocean. So part of the places it's going to be darker even here. That means it's even more difficult. It takes many more hours. The hours here are listed between 1 to 3 hours, and you just can't get there. So this dark area now is a lot smaller for the ocean part, but we see some places it's picked up. Maybe the internal rivers are not frozen yet, so you're really isolated, and that would be this dark places here. So these kind of changes are happening. Some places it's good if you worry about transportation. Some places it's not so good. The warming, the change in Nature Climate Change, which is a journal. So I thought I'd show you a couple pictures of ice. This is a satellite, the MODIS satellite, in June of 2008. And I just labeled Barrow to show you where it is. And lots of ice. It's not just a beautiful white sheet. It's broken up. It's moving around. Is that the time of year for whales? I can't remember. June. Not a whaling time. Here is farther along to the east in the Arctic coast, Arctic National Wildlife Refuge, and I just think that this is a very dynamic view of the ice movement out on in the shallow waters of the coast. And then we have the Arctic coastal plain, we have the Brooks Range here. And that was a time when, in fact, if you looked at where the ice extent is, it would appear, oh, there should be lots of open water. Well, the wind was wrong, and obviously, if you're on a ship, you'd be in trouble right there. Glaciers are retreating in Alaska. They've been retreating for a long time. Here is there are records from this site here, Glacier National Park, going back to 1794, when Captain Vancouver discovered the place, and the ice has retreated 60 miles or more. So that, and the Muir Glacier is retreating quite rapidly. Pictures on the left. Pictures on the right are small glaciers in the Brooks Range, 1958, and that was the IGY year. There was a station up there. I actually landed on an airplane up on that glacier in 1958, and 2002, there's been a lot. By 2002, there's been a lot of pullback, glaciers retreating. But not all Arctic glaciers are receding, and the contrast is between the total Arctic glacier volume here, which would include those other pictures, and then the Arctic glaciers in Europe that are actually increasing at this time. Spruce beetles, spruce bark beetle in Alaska and in British Columbia, other places are having a tremendous effect on this resource. And it's in Alaska, it's really their central and northern, it's really their only resource of trees, forest. And so 2 years, 72 to 85, contrasted 85 to 98, the spruce beetle outbreaks, and these are millions of acres here are being affected. I think the number was 4 million acres in the state. Well, why did that happen? One might ask. And it would be nice if there were just a nice smoking gun, but it didn't work out like that. People who've been studying this say, well, the insect is heat limited in the summer, so that when it's growing, and normally requires 2 years to complete its life cycle. When it's warmer, as it has been, then it reproduces in 1 year, so you can certainly get response faster. And so that is happening. But then if there are cold winters, 2 successive cold winters will reduce survival by a lot. So that's another way that the spruce bark beetle is limited. It doesn't have any outbreaks. So now we have warmer winters and warmer summers. So both these things are happening. Because of the ice has drawn back in the summer, then if there are coastal storms, then in fact the storms and the waves have a lot more open water to build up, and they can have a tremendously bad effect on the coastal villages. And here, this dark line here is the open water, and we see in the recent years, in 1980 on, there's been a large increase in the number of storms, these summer storms, when in fact they can be really destructive storms. Erosion. And here is a village, Newtok, and the Army Corps of Engineers is predicting that the coastline is going to retreat hundreds of meters over the next 30 years, 20, 30 years. So it's really a big change, a big effect, and we haven't even talked about there will be a increase in the height of the sea level. That will be coming more and more too. How about fire? Here's been warmer and drier in some places. Well, these are places in Alaska where, in fact, the fire has been, this is a 56-year record. And we see it's in the central part of Alaska, out to the Seward Peninsula here. But there's practically nothing in the Arctic. Fire has not been a problem at all. But the area burned is projected to triple under moderate greenhouse gas emissions. So not only is this losing the resource, the forest, but also there's a tremendous public health problem of air quality. I was in Fairbanks 2005. You couldn't see more than about 200 feet. It was really, really thick there, and it went on and on and on for a number of months. So that's going to happen even more. The Arctic didn't have any. We said, oh, it's too moist up there in the tundra, and we don't have many lightning storms. Well, 2007. This happened. There was a dry spell, 2 or 3 or 4 weeks, and there were a number of lightning, and there was a lightning storm. And there, 30 miles away, there was a large fire. Well, here is the fire in 16th of July, and then we see clear weather, and 2 hours, 3 hours later, it clouded up. The smoke blew this way, and in September, it was burning here. These are wimpy little fires, though. You couldn't even jump a river at all because the canopy, the forest there is a foot high. But there's a lot of, don't forget, there's a lot of carbon in the soil, tremendous amounts. And by 30th September, the fire was still burning. These white dots are frozen lakes. So it wasn't until the snow happened in early October that we finally got put the fire out. Well, here was an opportunity to study this. There was so much burn, so intense burn on the soil. The soil here, we can see a foot or more thick, has tremendous amounts of organic carbon. And that amount there is total over the Arctic is equal to 2 times the total amount in the atmosphere of the world. And here the fire was so intense it burned all the organic matter off and got down to the mineral soil, and it actually, iron at the mineral soil turned red and orange. It doesn't show up in with this projector, but that was what was happening, the oxidation of this iron. Well, Arctic vegetation here in Alaska is becoming more shrubby. How do people know? Well, there are some oil company exploration pictures from 1950 in the same scene 50 years later. Now, it's not an overwhelming bit of evidence. If you look at any place, yes, there are. It is a little bit denser, the shrubs there, but are these the same shrubs just getting a little bit bigger, or just what is happening? And so that's still a very difficult question, and people are still arguing. It's sort of the state-of-the-art discussion. And I point out that the willow, birch, and alder shrubs grow slowly anyway, and they can live for over 100 years. So a little bit of warming is not going to suddenly cause these things to just wilt. They actually would grow better. We wouldn't expect a really fast response to these small changes that have been seen so far. But then the satellites came into being, and part of Alaska is green, we see up here, and part is brown. So this is a cumulative, it's actually showing what's happened with a greenness index that they can measure from a satellite. And we see up in this part, in fact, it's greener. It really is greener. And here, it's browner because of all the fire and the drought that's been going on. So, so what has been measured really is the amount of reflectance of different wavelengths, and they put that into a formula and come out with a biomass. We can calibrate how many grams of carbon there are on a meter squared. So it is a integrating measurement. And of course, from satellite, you're not just measuring a square meter, you're measuring many more square meters. So that's happening and going to continue. We don't know whether that's just more leaves, or whether the whole plant is or more separate plants. So that work is still underway. Here's a picture of alders growing on the north slope. Isn't that a great picture? What it is polygonally patterned ground. And these are, we call these polygons, these little places where ponds have formed. There's a little bit of raised outline. And that is because of permafrost, and that is because of a little height difference there, just a centimeter or two, that allows this shrub to grow. This is a nitrogen fixing shrub anyway, so it gets a big kick because it can organize its own nitrogen. So I haven't mentioned permafrost yet, and yet it is the most important part of the whole picture here. So now we're going to have more than you want to know about permafrost. Frozen ground, that's simple. It isn't, it can be ice, it can be a gravel pile, sand, it can be dry, and 22% of North America is underlain by permafrost. It's frozen ground under there. And here's where all this soil is, the carbon is. I mentioned the big number here, 1,600 petagrams, and that's what a petagram is, which is 1 billion metric tons. It's a big number, and that's about 2 times the total amount in the atmospheric pool, the carbon. So don't want that to get warm and decompose and go off as CO2. That would be bad. So what controls all this? I mentioned before that there's continuous permafrost, and that's up in the northern part of Alaska, discontinuous permafrost here, and then sporadic. Over in Siberia, there's a tremendous amount of continuous permafrost. The farther you go away from the Gulf Stream, the more permafrost that there is. Here's what it looks like on a transect starting up in Prudhoe Bay and going south. Permafrost is 1,800 feet thick there at Prudhoe Bay. And the active layer, the part that melts every summer, is not part of permafrost, but it's an active layer where all the roots and plants live. That up there is 20 to 35 inches thick. Okay. Then we get down south, Fairbanks. We see here 1 to 1.5 meters, 60 meters. This is a discontinuous, so it's on the north-facing slopes. It isn't on the south-facing slopes. And then finally down in the Chickaloon, and my wife says, "Where's Chickaloon?" So I looked it up. It's next to Wasilla. So now everybody knows where Wasilla is. You wouldn't have known that before. Right down near, not too far from Anchorage. And that's the permafrost is getting pretty discontinuous. And is, of course, that part is going to lose all its permafrost because it's really warm right at the melting point now of water. There's an easy metric here. They have 6 or 8 deep boreholes drilled along the road, along the pipeline road, and this is the farthest north one. You put oil, fill this hole with oil, and measure down. We just drop a thermistor down and measure that, and this is what's happening at 65 feet, where you don't see any annual change. It's down where the changes are long-term changes going on. Okay, and we see a change from 17 Fahrenheit, and now it's warmed up to 22 or 23. Well, it's getting up there towards 32. So bad things happen when permafrost gets warm up to the freezing point. There is a threshold there. And a lot of Alaska up on the North Slope is underlined by ice wedges. This is something, you can see the results of ice wedges. You can't see ice wedges unless you hit something where there's been a part of, something fell off into the ocean, or a road was built. And the ice wedges begin to form when the tundra really gets chilled during the winter, and there's a crack that forms. And this crack is just like cracks in a mud puddle or something due to drying. And they can form whole polygons that will be hundreds of feet across. And then water comes in the springtime and enters the cracks and freezes when it reaches the permafrost. So after 100 years or 1,000 years, you have a giant ice wedge underneath here that may be 10 feet across or so, 5 feet across. And they're all connected in this network, and there's a little bit of an ice push ridge up above. So forms a very nice container for a little tundra pond. Okay? And here is one picture. We already saw all those alder trees sitting on the little ice push ridges. Here is a ice wedge on a coastal small cliff, Barter Island, and this white stuff is not the white cliffs of Dover type of thing. This is ice here along one edge of one of these giant polygons, and here it even has a nice ice wedge shape. And so here that's begun to melt, and this whole block has fallen off. So the erosion is not a gradual thing. This is something that happens in a big storm. Near Barrow, the entire coastal plain is covered by old lakes. And on those old lakes, these little tundra ponds have formed due to the ice wedges. We see tremendous here. So here's an old pond, here's an old lake, here's an old lake here, another big lake here, and thousands of ponds. We did research on some of these ponds for 3 years back in the 70s. And here is one of our research. We had so many people trying to work on that pond that we had to put in aerial tramway so they wouldn't tromp around and break up the ecosystem. People are going back there now. This year I was up there for a while advising a project that's making some of the same measurements again of the algae and the phosphorus and the growth of all these plants. So that's a picture from 72. This part up here is the active layer, 31 inches, where the roots, plant roots, can grow. And we see below that massive ice wedges. So the problem comes when the ice wedges melt and the whole system collapses. And we see here's a picture of a person standing in here, hidden. And you see collapse of a boreal forest, probably in Siberia. In Fairbanks, giant, melted out just along the road. Some of these trees where the permafrost has thawed, or the ice in the permafrost has thawed, and so it looks like a drunken forest. Here's a nice house here in Fairbanks, or somewhere like that they weren't too careful about where they sited it, and there was ice underneath. And this is Chersky in Russia, or one of the Russian villages where, in fact, you'd think they would have known better, having lived there for a long time. But anyway, a big breakup. So there's a threshold here. And this is the Alaska highway map. Each dot is where the highways are, and these are all on village in towns and villages. This is the paved highway system, which is 4,900 miles. These are the only connected parts of the system. So there is no road net. There's just a very limited area. And this area here is the part that's going to be affected by this permafrost. If the permafrost and ice is under a airfield, terrible problems. Under a road, terrible problems because of melting. There's a road at the University of Alaska, Fairbanks campus, where the road comes down to a main road from their bluff, and there was permafrost under there, so it thaws a little bit, and then they put asphalt there, and it happens again, you put asphalt. 25 feet later, things have stabilized, but they got 25-foot thick piece of asphalt sitting there, built up over the years. And some of the costs estimated by 2080 would be $6 to $7 billion for future cost for publicly owned infrastructure. And here is a little scene where a road has slumped. That's a big pothole. Some parts there's going to be ponds and lakes being lost, but not in the Arctic for the next 100 years because it's still cold, and the ice is still cold, permafrost is still cold. When they built the oil pipeline, they had to keep 50% of it above ground. 50%. And they would much rather have put it all underground, much cheaper. But they were worried about where there was ice and a hot oil pipeline at 140 degrees centigrade, 140 centigrade, no, 140 Fahrenheit would melt some of these holes, some of these ice, and some of this ice, and there would be collapse. So it's all above, 50% above ground. And in the Seward Peninsula, currently, it's going to be discontinuous, and then later this century, there will be only almost all the permafrost then will be discontinuous, and a lot of areas there won't be any permafrost. So what do scientists measure in all this? And I thought we'd just finish up by talking a little bit about what can be measured and the value of long-term ecological records and long-term experiments, because that's what the scientists have been doing there. We started research at this one site on the North Slope in 1975, the year they opened the pipeline road. And so here is the pipeline road up here. That's the road, and that's the pipeline coming in. And 135 miles south of Prudhoe Bay. So it's called Toolik Lake. And the field station is now run by the University of Alaska. We have up to 100 scientists there at one time, and the people change and come in for a week. People come in for the summer. So there's a lot of different projects there. Our long-term ecological project is just one of these now. Used to be the main one. We have a website. If you want to find out what the temperature is right now, today, just go at the website and find out that this is dates here, about 6 or 7 days worth, and temperature last Friday or something like that was right up at freezing, and had some cold time. Here, lake temperature dropping. The lake probably froze again last week, and then solar radiation, etc. And here's the address. You can go and look at data till you're blue in the face. But with all this high tech and websites and everything, we haven't been able to demonstrate that the air temperature has changed in this place. It certainly is changing from year to year to year, but to try to figure out whether this is a trend or not, you need a lot more data. Our 25 years is just not enough. So that would be a direct measurement, and certainly is what we would expect to have happen over longer periods of time in all the climate models. Yes, it's going to happen over longer periods of time. But the ground is snow-free for 2 weeks longer now than in 1989. So we see this graph here. Yes, the growing season length is longer. That's one thing certainly we can count on that's happening. And one change that we can't argue with is an integrating change, and that is a chemical change in the water, in the stream water and in the lake water. It's a change in the alkalinity of the water, and in my opinion, this is a good proxy for increased permafrost thaw. Well, what that means is just at the bottom of the active layer, top of the permafrost there is in glacial till. It's been frozen there for 10,000 years, that glacial, that till, and it has a lot of carbonates in the soil. So now there is some weathering going on, interaction between these carbonate minerals and water. And so the alkalinity, which is mainly carbonate, is showing up in the soil water. We don't know where it's happening. Is it happening just in the top few millimeters of the former permafrost, or is it underneath some stream places? We just don't know yet, but there's also some stable isotope changes. So, and this amount of change is not anything that's going to affect plants or animals. It's a proxy of what is happening in the soil. So we have evidence of increased permafrost thaw, but when we try to measure the thaw depth, go out there twice a year and measure 1,000 points, well, it's a mess. It varies from year to year to year. There isn't any change, except up at Barrow, where it's a lot colder, these numbers would be down deeper. There's less thaw there at Barrow. Okay. Set up a grid of posts where we had measured exactly where they were, and every 6 years go out and do a survey looking at a single square meter here next to each one of these posts. And these posts, they have 109 of these posts. Tremendously detailed work, and they measure here the shrubs, the grasses, the mosses, lichens, forbs. It's called a point frame, and they put down little sticks and see where one of these actually hits a plant. So they're looking at the same grid every 6 years. And here from the one from our Tulik site, it in fact is getting more and shrubbier and shrubbier, higher and higher biomass over time of the shrubs. Grasses, well, as things are falling, here was an increase and now a decrease. Mosses are way down. So we have records here from 1990, 96, 2002, 2008. Tremendous laborious work of trying to figure out what's happening. Where is this change happening? And what are the implications for the future? Long-term record, here's nitrate in our nearby river. And we see a big change from 2002, 2005 is the blue. That concentrations are higher than they were back in the 70s and the 90s. So we have records like that. We don't know why this change is happening. It certainly is happening, and it's a very important one, runoff of nutrients. Finally, we actually go out there and change the environment. We do experiments with these systems. And what do we change? Well, here we're changing nutrients, temperature. These little greenhouses are for changing temperature. They come down in the fall. The dark ones, that's shading light. That's 50% of light taken off. Change the pH, put little wire fences there to keep out the caribou and the mice and everything that's eating the tundra, and do the similar changes with lakes and streams. Added nutrients to take away fish. We begin to get an idea of the processes that are controlling these systems. Why aren't there more fish? Why aren't there more plants? Why isn't there better plant growth? We can test a lot of this. And here is, for example, one of these greenhouses. And on the left, we see the birch in the warming and fertilized experiment. Those birch used to be 1 foot high, and now they're about 4 feet high. And that's warming plus fertilizer. They're actually up 6 feet high. And in just the warming alone experiment on the right, they aren't up that high. They're only up 2.5 or 3 feet. They've responded probably through the microbes breaking down more organic matter in the soil, providing more nitrogen. So that's the kind of experiments that we can do, and certainly tundra does respond. Here is the birch responding without any heating. And the birch responds so well that, in fact, pretty soon, after a number of years, started out in 82, they have grown so much that they've completely shaded out everything else in the plot, so that's the experiment sort of ends. And do experiments, weeding, leaving only certain species. How do the species interact? And in streams, there's been a drip of phosphoric acid in this river since 1982, and the river was dominated by sort of a little bit of diatom growth on rocks. That's what makes rocks slippery if you're trying to walk in the river. And here the mosses have taken over. So we had tremendous growth of mosses. We didn't even see them before. They were certainly there, but we didn't even notice them. We were about to give up the whole experiment, and after 9 years, then all of a sudden this gigantic change happened, and the whole river is changed, at least for that half a mile or so where there's enough phosphorus. Finally, talking a little bit about a fire, and I mentioned lightning strikes on the north slope. Here is what this particular storm looked like. BLM is able to record the location and occurrence of every lightning strike in the whole state. And so they know where to look for the fires. Not that they're doing anything about them, but they know where to look for them. And the strikes have increased 10 times since 2000. Why is that? Because of more open water and more storms, as we saw, moving through the system. And so we had one big fire. I've already mentioned the picture here from the satellite. Well, the burn, here's a severe burn, and here's a moderate burn and unburned tundra. We are looking here at the amount of carbon dioxide coming off the system. A very sophisticated flux measurement. And how much soil plant carbon was lost? A lot. 2 of these teragrams, which is 1 billion kilograms of carbon, was lost in this one fire, which is 1,000 kilometers squared. But the whole tundra, well, that's growing better, perhaps. Isn't it socking away some of this carbon in the sequestration? Well, that complete change here of more carbon was, for this whole big river basin, was only 0.2 of these teragrams. So this little area was 2 teragrams lost. This whole area was 0.2 teragrams. Was socked away, sequestered. Well, so it's a very important process for changing the tundra, and it's happening faster and faster and faster, we think. Finally, the interactions here, this doesn't just happen at Toolik Lake or this region and the ocean. We see more melting of the sea ice and more radiation is absorbed. The ocean is warmed and more melting of sea ice. So it's a nice feedback here. On the land, the vegetation grows faster, more shrubs, more radiation absorbed, earlier snowmelt, and we see, again, positive feedback. All this Arctic warming goes faster and faster, and the global warming also is a part of the whole here, but it's probably happening faster in the Arctic than any other place. Just to summarize some of these things going to happen in the future: ocean ice, 50 years, ice-free Arctic Ocean. Northwest Passage and Northern Sea Route will be open. Climate and continue to moderate. Growing season lengthened. Precipitation increased by 38%. Maybe. That's the most doubtful projection there. It's very difficult to get. The models don't even get the present precipitation right. And here we're talking about what's happening at the end of the century. Fire, more frequency, we think. Permafrost disappears for most of Alaska, but it's stable on the North Slope. And we mentioned the damage, road and airfield, but not on the North Slope. More erosion and permafrost, coastal erosion, much as 200 meters over the next century. And lakes and ponds, some will disappear. Vegetation, better grass and sedge growth, but dwarf birch and alder will spread. Caribou don't seem to like dwarf birch, so that might be there's a lot of resin in these leaves and branches, so that could be bad. Fish, some are not going to survive, it's too warm. Large mammals, more roads, development, and more hunters and other disturbance. Takeaway message is just 3 points here. Changes are very slow in the Arctic. Despite warming air temperatures, plants are long-lived. Changes will occur, species abundance, and not by species replacement. There's no sign of that. Permafrost, tremendously important in shaping the ecology of the tundra. It affects the drainage. The water stays up in the upper parts of the soil, so it's a moist tundra, and yet I didn't mention that, in fact, the total precipitation is more like a desert. And it will be a century or more before the thawing threshold is reached in the Arctic. Finally, a good way to understand what's happening and make projections to the future is by experimental manipulations of nutrients, heat, and species, a valuable tool for ecological prediction. So thank you for your attention.
We have time for a few questions, and we're recording this, so please use one of our microphones here if you have a question to ask.
Very nice, John. You've done a great job since you graduated with our class. Listen, I wanted to, shortly after you graduated, you did some research in Greenland with ice cores and things of that type. Did you end up identifying any other serious climatic changes in the past that were of this type of magnitude in terms of duration and intensity?
Well, our type of research that we're doing could not answer that question. We were more interested in lakes. This was a Cold War, so we were working out of Thule. We wanted to know if those fighters and bombers with atomic bombs could actually land on an Arctic lake as an emergency landing strip. So that was Dartmouth's contribution. And the answer was no. It's still too rough. But
you said that the depth of the permafrost hadn't changed, but that there was more carbonate in the waters. And so I'm just wondering if you're still deducing that that carbonate came from the permafrost in some way.
It's just our lousy measurements of how thick the active layer is, how it changes. It's just when there are tussocks on top, which is the growth form of a lot of these sedges, and the thickness of the so you're measuring along this transect, and you put a iron rod down and you hit ice, you hit the permafrost, and so then you're going along and it's that way, and then you're under a tussock and bang, the tussock has insulated things, and then next to it, or maybe next to it, it's back down, or something else happened. There was a little snow bank there, so it's just so variable trying to get good data, fine data on that kind of measurement. So it's our measurement, not whether or not it's happening. So that's why the chemistry was more of an integrating measurement. It measured something happening over a much larger area.
The fires are really spooky. What are thoughts about recovery from areas like that where you've burned down to the mineral soil? What are the predictions?
Well, I don't know, because in fact I'm not a fire ecologist, and the fire and its recovery has been a major effort in the interior of Alaska, but as you see, not on the North Slope. Certainly a moderate burn, the tussocks, you think they're all dead, but bang, within weeks they've started to sprout again. So strong recovery, but how long it takes to build up that organic soil again. I'm sure there are other people who would talk about it better, and people at the University of Alaska Fairbanks. There's been some big projects about burns, but not in the Arctic. Yeah.
A couple of years ago, I attended an international Arctic Year conference here, and I remember a fellow standing up near the end of one talk that may have been in this room, and he looked very grim, and he discussed the fact that when the waters open up, there will be international disputes over resources. And what level of international cooperation is there up there to preserve the environment?
International cooperation. Let's see, I can tell you about the Antarctic for a long time.
Isn't the international LTVR?
Well, but as far as anything across governments, there's certainly cooperation of scientists and projects sharing data, but right now the argument, because the U.S. never signed the law of the sea, right? So the next step, I think, is that other countries are making their claims, and there was a limit of when they had to end making claims, and that's already passed now, and the U.S. still has not signed the law of the sea.
Why have they not signed it?
We don't sign treaties.
Especially environmental treaties.
Environmental treaties.
May I ask one other question about the Arctic coastal plain, the last 90 miles, and it's still preserved, the last undeveloped 90 miles next to Canada? What's the potential for oil drilling to stay out of that section?
Depends who wins the election, I think, in part, because that's part of that just up right near the ocean is where this Barrow Arch geological system that they think contains the oil. But they haven't done any drilling in that region, so they can't really say whether that's true or not. So I don't really know what the chances are. But it is the last wilderness, and certainly the setting up ANWR, the wildlife refuge, was a tremendous victory for conservation in the United States 50 years ago, and we certainly hope that some of that country is not changed. But when that does happen, then there's all sorts of movement of grizzly bears and wolves flocked into that area. It's not just a little patch where the drilling might be, and they're much better at drilling now than it used to be in terms of area, but then you've got a road and the hunters, and pretty soon the state takes it over and become available for all sorts of people. There are less than 1,000 people that go into that area now a year.
Do you have any favorite possible explanations for the increasing nitrates in the streams?
Well, yeah, it's a good question. And, I said we didn't know, but atmospheric deposition is not a question up there. There is practically none, and so it's not atmospheric deposition. The soil is warmer, and we see that when we warm the soil, we do get more nitrogen available, but as shown by the growth of these nitrogen-limited shrubs. So that sort of logic would say the nitrogen cycle is being enhanced. Things are happening faster. That's a question for you to do research.
Well, I think that John is a great example of the value of liberal education, at least the way it's for.
Oh, right.
All this has been accomplished, we're going to claim much of it.
I think it's Berkeley.